It really all comes down to this one question. What is light? I mean, really, what is it made of? Is it a stream of tiny little bullets shot out from a source? Or is it more like a ripple spreading through space? This seemingly simple question started a scientific rivalry that lasted for centuries.
So two major camps formed. On one side, you had the idea that light is a shower of tiny individual particles, kind of like a spray of microscopic paintballs. And on the other side, you had the theory that light is a wave of vibration moving through space, a lot like the ripples you see when you drop a stone in a pond.
Okay, let's start with the first heavyweight champion in this fight. Because when the most famous scientist on the planet picks a side, you better believe people are going to listen. And the man himself, Sir Isaac Newton, he picked particles.
So back in 1675, Newton laid out his corpuscular theory. His big idea was that every light source, from a candle to the sun, is basically shooting out a constant stream of what he called corpuscles, these teeny-tiny, massless particles that travel in perfectly straight lines.
You have to understand, Newton was an absolute giant in the world of science. His reputation was so huge that whatever he said, well, that was pretty much the final word. So his particle theory became the accepted truth for more than 100 years. It was easy to picture, it felt intuitive, and honestly, it seemed to explain a lot.
But Newton wasn't the only one with a big idea. There was a rival scientist who had a completely different take, and this really set the stage for a major scientific showdown.
I get this. 10 years before Newton even published his theory, a man named Robert Hooke came out with his pulse theory. He argued that light wasn't a thing at all. Instead, it was a vibration, a series of pulses moving through this mysterious, invisible substance that they imagined filled all of space, something they called the ether.
So, Hooke was the main guy championing the wave idea. And let's just say he and Newton were not friends. They were famous rivals, and this disagreement over what light actually was became one of their biggest and most bitter fights.
And you can really see their two theories clash when you ask them to explain something as simple as color. For Newton and his particles, it was all about size. Red light was made of the biggest corpuscles, and violet light was made of the smallest ones. But for Hooke and his waves, it was all about frequency. Red light was a low-frequency wave, and blue light was a high-frequency wave. Two totally different explanations.
For a very long time, Newton's theory was on top, but the evidence for waves just kept building. Scientists discovered that light could actually bend around corners, a phenomenon called diffraction. Particles just shouldn't be able to do that. Then they discovered polarization, which proved that light waves vibrate side to side. By the late 1800s, the fight seemed to be over. The evidence was overwhelming. The wave theory had won.
Or so everyone thought. It really looked like science had this all wrapped up. And then, one single stubborn experiment came along that just didn't make any sense. It was a result that nobody could explain, and it was about to break everything. The name of this troublemaker was the photoelectric effect, and the idea behind it is actually pretty simple. If you shine light on a piece of metal, you can sometimes knock electrons right off of it. Now, the wave theory made some very specific predictions about how this should work, and every single one of them turned out to be wrong.
This is where the whole thing just falls apart. The predictions from the wave theory, what scientists were sure should happen, are over there on the left, but what they actually saw in the lab, well, that's over on the right. It was a completely different story. Let's break down just how big this disaster was for the wave theory. So failure number one, the frequency problem. The wave theory basically said that any color of light, as long as you made it bright enough, should eventually build up enough energy to kick an electron out. But the experiment showed that just wasn't true. It turns out every metal has this threshold frequency. If your light is below that frequency, say red light, you can crank up the brightness and leave it on for 1,000,000 years, and absolutely nothing happens. Not a single electron moves.
Okay, on to failure number two, the energy problem. The wave theory predicted that a brighter, more intense light, like a bigger ocean wave, should hit the electrons harder and send them flying out with way more energy. But again, experiments showed the complete opposite. Turning up the brightness did kick out more electrons, but each one of those electrons had the exact same energy as before.
So here's the absolute killer. The energy of the electrons getting knocked off had nothing to do with the light's brightness, its intensity. No. Instead, it was all about the light's frequency, its color. A high-frequency blue light would kick out high-energy electrons. A lower-frequency yellow light kicked out lower-energy electrons. This wasn't a small mistake. This was a complete violation of everything we knew about waves.
So physics was completely stuck. The wave theory, which had been so triumphant, was now broken. The science world was in crisis. And then, in 1905, a young patent clerk you might have heard of, Albert Einstein, came up with a radical idea that brought Newton's old particle theory roaring back from the dead.
Einstein just said, what if we've been thinking about this all wrong? What if light energy isn't a continuous, spread-out wave? He proposed that light actually comes in little individual packets of energy. He called them quanta. Today, we call them photons, but you can just think of them as tiny little bullets of light.
And just like that, this one simple shift in thinking solved everything. The energy of a single photon bullet depends only on its frequency. That explains the threshold. If one little bullet doesn't have enough energy to do the job, it doesn't matter how many you fire. The energy transfer is a one-shot deal. One photon hits one electron instantly. And a brighter light? That's not a bigger wave, it's just more photon bullets being fired, which knocks out more electrons. It was perfect. It explained everything.
So, is light a particle, after all? Was Newton right this whole time? But wait a minute. What about all that evidence for waves? What about diffraction and interference? The answer that science finally settled on is maybe the weirdest and coolest thing in all of physics. The final answer is both sides were right. Light is a shapeshifter. It has this bizarre dual nature. When it's just traveling through space, it acts exactly like a wave, spreading out and creating patterns. But the moment it interacts with something, like hitting that piece of metal, bam, it acts like a particle, delivering all its energy in one tiny punch. It literally has two completely contradictory faces, and it chooses which one to show us based on how we try to measure it.
Our most up-to-date theory, quantum field theory, ties these two wild ideas together beautifully. So try to picture an invisible field that fills all of space. A ripple moving through that field, well, that's a wave of light. But here's the quantum twist. The field is quantized. That means its energy can only exist in specific, countable little packets. And one of those individual energy packets is what we call a particle, a photon.
So this 300-year war over light didn't end with one side winning. It ended with a truce that revealed that reality is so much deeper and so much weirder than we ever imagined. It really makes you wonder, if something as basic as light can be two opposite things at the very same time, what other fundamental rules of our universe are we just completely wrong about? What else is stranger than it seems?